Hi, welcome to AB Video 5.5 Part 2, the end of derivatives and integrals involving other exponential functions. Okay, so now we're going to do some calculus with these exponential functions. Find dy dx, y equals x times, they won't put that times there, they'll just put a parentheses, but that means we got a product rule. So we have the first factor times the derivative of the second factor. So this is the derivative of a to the u is a to the u times ln a times du dx. So it's 6 to the negative 2x times ln 6 times the derivative of the ugly exponent negative 2x, which is negative 2, plus the second factor times the derivative of the first factor. At this point, you could factor out the 6 to the negative 2x, leaving you with x times ln 6 times negative 2 plus 1. I'm not going to go any further than that. Here is y equals log base 10 of x squared minus 1 over x. One of the first things you can do is you have the log of a quotient, so you can split it up into a difference. Personally, I would then change everything, do the change of base to get it into ln. So that's ln of the top over ln of the bottom minus ln of the top over ln of the bottom. 1 over ln 10 is a common factor and it's a constant. So I pull that on the outside. I'm left with ln x squared minus 1 minus ln x. Now we'll take the derivative. Notice how many steps before we actually start taking the derivative. So the derivative of, it's 1 over ln 10. Derivative of the ln of a thing is 1 over the thing times the derivative of that thing. Same thing here, derivative of, and there's your answer. Find the equation of the tangent line to y equals log base 10 of 2x at the point 5, 1. Again, I would change the base, ln 2x over ln 10. We have a point, of course, need a slope. The slope is dy dx. So I'm going to need to take the derivative of this expression right here. I'm going to pull out that constant of 1 over ln 10, and I'm taking the derivative of the ln of 2x, which will be 1 over 2x times the derivative of 2x, which will give me 1 over x ln 10. Now I want it at the point where x equals 5, so that's 1 over 5 ln 10. And then I plug in my point and my slope into this point slope formula. Number 76, we're integrating 5 to the negative x. Well, that's ugly, that negative x, so I got to let u equal the exponent, which is negative x. My du will be negative dx. Introduce the negative counteract. And now you're looking at 5 to the u, because remember we let u equal negative x times du, which will be negative. We had that from the outside. 5 to the u over ln 5 plus c, and then you can't leave your u, you have to rewrite it as x. 82, same idea, let u equal the exponent, so u is equal to sine x, and how convenient for us that the du is cosine x dx, which is exactly what they gave you. So we're actually integrating 2 to the u du, which is 2 to the u over ln 2 plus c, and then I replace the u by sine x. Number 84, we're going to let u equal the exponent again. The derivative of that is 1/2 dx, so I have to introduce the half, counteract with multiplying by 2 over 1. Now I'm going to integrate, so I have the 2 times the integral of 4 to the u du now, which is going to give me 2 times the integral of 4 to the u du is 4 to the u over ln 4. Which will give you 2 times 4 to the x over 2. Replace the u by x over 2. And now we can substitute. You got to understand that when this says dx, that automatically implies that this is from x equals negative 2 to x equals 2. You couldn't stop, for example, here with the u and say from negative 2 to 2, because that wouldn't work. Okay, so we plug in the top number. We get 2 over 2, which is 1. So we get 2 times 4. Oh, I'm going to pull the 2 on the outside. So we have 4 over ln 4 minus. Then I plug in negative 2. That'll give me 4 to the negative 1, which is 1 over 4. And then I have my ln 4 right there. Okay. All right, I believe this is the last question. I want you to see this question out of the textbook. This is number 110. Okay, so here's number 110, population growth. A lake is stocked with 500 fish and the population increases according to the logistic curve. You don't need to know what that means. So they gave you the function. That's all that matters, where t is measured in months. It says use a graphing utility to graph the function. What is the limiting size of the fish population? So here's the idea. You've got this lake, you've got 500 fish. You can't just deposit 4 billion fish into this little itty bitty lake because they will all die, because they won't have enough oxygen, because there won't be enough water for all of them to have enough oxygen to survive. So the limiting size means as time goes on, obviously these fish are going to reproduce, but they'll only reproduce to a certain point and then the population will stop growing because there just won't be enough food to sustain them. So limiting size really means the limit as t goes to infinity is what that means. Okay, so the limiting size, so here's the graph on your calculator, by the way. The limiting size is as t goes to infinity. So you got to figure that this e to the negative t over 5, you could rewrite as over e to the t over 5. If I replace t by infinity, infinity over 5 is infinity, e to the infinity is infinity. Think of the graph of y equals e to the x, right? And then 19 over infinity would give 0. So that's 1 plus 0, and you have a 10,000 on top. It means that your horizontal asymptote, basically, the limit as t approaches infinity, that's what your population of fish will approach, okay? Part C, at what rates is the fish population changing at the end of the first month and the 10 at the end of 10 months? So the rate of change of the population is the derivative of this function. So I took this whole thing and brought it to the top, made it -1. This is a constant. And then I have -1 times this expression to the -2 times the derivative of that expression, which is 0 plus 19 times. And the derivative of e to the u is e to the u du dx. And so it turns out that it's this ugly thing right here. And they want to know what is that rate of change at 1 month and at 2 months. So you would use a calculator and plug in t equals 1 and then plug in t equals 10. And then the last question that they're asking is, after how many months is the population increasing most rapidly? So increasing most rapidly is actually the point of inflection, because if you look at the graph, right, it's increasing slowly, then it starts to increasing very steeply, and then when it reaches the point of inflection, it's no longer increasing now. I'm still increasing, but it's increasing at a decreasing rate. It starts to level off. So that's the point where it increases the fastest, which is the point of inflection. Then you'd find the second derivative.